Let's talk about the sun. All right, so lecture today is going to all be about. So we are ready to start talking about other stars, and no, we're ready to start talking about stars in general, and we're going to start with the one that we know the best, and that is our sun. It is going to be our prototype for understanding how stars work. You're going to see here that there is a lot of details about our sun that apply to every star, and some details that only really apply to our sun. In particular, the exterior of the sun, like what you see in the picture here. See on the surface of the sun, seeing a big prominence come off of the surface of the sun. Those are details that we can see for our sun, and presumably those are details that can be seen on other stars as well, but stars are so distant and so small that at the distance that we are from them, we can't see these kind of details. So that stuff exists for other stars, but we can only really know that for the sun. And then there's details about the interior of our sun that are very interesting. Where nuclear fusion takes place, what powers the sun, and we can't see inside of the sun. So these are details that would be true of pretty much every star. So here are some general properties of the sun. We say our sun is a median star. Now I use that word specifically, median star, as opposed to saying that our sun is an average star. The big difference between the word average and median is average takes into account how often something occurs, where median just looks at the various values that one can have for something, and that kind of lies in the middle. So what I mean by that is, say, for example, the temperature of our sun. The surface temperature of the sun is around 5800 Kelvin. And that's kind of in the middle of all the various types of temperatures you can expect for stars. Plenty of stars have colder temperatures and warmer temperatures. And so in that sense, it's a median value. It's not an average value because the vast majority of stars that exist, at least in our galaxy, are not as hot as our sun. Like 90% of stars are cooler than our sun. So in terms of an average, our sun would be a little uncommon in terms of its value. But for all its other properties, it is pretty much in the middle. It's in the middle in terms of its brightness, temperature, size, mass. These are all things that are kind of in the middle. The only thing really about our sun that makes it very unique is that it is right next to us. It is extraordinarily bright in terms of its apparent magnitude, and that's because it's so close to us. In fact, it's difficult to imagine what our sun would be like if it wasn't so close to us. So we have this concept that I mentioned here, absolute visual magnitude. Now, this is something I'm going to formally define in a few lectures from now. But what this means is this is how bright our sun would be. So its apparent magnitude if it were located at a distance of 32.6 light years, which is 10 parsecs. And that's not very far away, by the way. Tens of light years is right around the corner, honestly. And its magnitude would be close to 5. Now, I don't know if you remember about magnitudes, but the magnitude system for light that the eye can perceive goes down to around magnitude 6. Magnitude 1 stars and 2 stars are very easily seen in the sky. Like in the Antelope Valley here, we could see probably down to magnitude 3, maybe even 4 if you're in a really dark area. My point is this. With the sun being 5, if it was pushed out with all the other stars, we wouldn't even see it. It wouldn't really be visible to us. So our sun is very bright because it's close, but it's not extraordinary in its brightness. Put it that way. how extraordinary its brightness. In terms of its size, you can fit 100 Earths from in the diameter of the sun, and that means the surface area of the sun is 10,000 times that of the Earth, and the volume of the sun is 1,000,000 times larger than the Earth. Okay, the sun represents 99%, basically 99.9% of all of the matter in our solar system. Down at the bottom here is a important point: the surface temperature and the central temperature. Inside the sun, at its core, is a temperature of 15 million Kelvin. That would be just shy of 30 million Fahrenheit. And those temperatures are sufficient to cause nuclear fusion reactions, which powers the sun. And in fact, I will show you a little bit of that today. All right. So here is a breakdown of the anatomy of our sun. There's a lot going on in this picture here, so on the side, I'm going to write out some things to sort of help you get the structure here. So give me a second to do that. Annotate text, make it white. So I'm going to list here layers of the sun, and these layers of the sun are going to be from the bottom all the way out to the atmosphere of the sun. The very bottom is the core. That is the area of the sun that is at the very bottom, okay, so to speak, the very center of the sun, where it's the hottest. So hot that nuclear fusion reactions occur. And that represents maybe 10 to 50% of the interior of the sun. As you go a little ways out from that, you get to a region called the radiative zone. This is a region that is very similar to the core in the sense that it is very hot and very dense, but being that it's a little further out from the core, it's slightly cooler, cool enough that nuclear fusion reactions are not taking place here. It is extremely dense because of all the gravitational pressure being applied on this interior region. So much so that material is not really free to move here. Things are sort of stuck, frozen, so to speak. Not obviously frozen in the cold sense, but immobile. And that's an important distinction to make because it determines how energy can flow from the core out to the surface. And we'll discuss that in a little bit here. The next region outside of that is what's called the convection zone. These are all interior layers of our sun. The convection zone, however, is when you get out to about maybe 70% of the radius of the sun, you get to a region where the conditions inside of the sun has relaxed enough. It's cooler, it's not as dense, and those relaxed conditions allow material to freely move in this area. So you can have gas that mixes and moves around. In fact, you'll see a little bit later here some examples of where we can actually see the motion of the gas rising up to the surface and sinking down, like the sun's surface, looks like it's bubbling basically. And that's due to the convection that takes place. All right, so these three layers here are what we refer to as the interior of the sun. So interior. There are three regions that comprise the exterior of our sun. And the first region that we consider to be exterior, and by the way, when I say exterior, I mean we can see these. And I'll show you pictures in a moment of what these regions look like. We have our photosphere. The photosphere is what we consider to be the surface of the sun. Surface of the sun. Now, it's not an actual surface like this desk here is a surface. There's a very clear boundary between the desk and the air. When we say surface here, what we're basically describing is this is the layer of the sun that starts to become opaque. It's a layer of the sun that you can't see deep enough into. And it's a true layer, it's not a true surface, I mean, in the sense that you can land something on it, you can see it. It's actually a rather thick layer, around 500 kilometers, which is where you can't see deeper into the sun. Too dense. Okay. All right. The next layer is referred to as the chromosphere. And this is the first atmospheric layer of the sun. Give me a second here. This is the first atmospheric layer of our sun. This lies right above the give me a second. What's going on here? This is the first atmospheric layer of the sun, right above what's occurred in the photosphere. This is where we see things like prominences, where we see things like the solar flares and stuff like that. And then there's an extended atmosphere called a corona. And I know that's not a timely term, but it's an old term. And the corona represents, it represents sort of like a wind that comes from the sun. And it actually looks like that in pictures. There's a steady stream of particles that are being ejected from the sun just because it's so hot, it has so much energy. It's not just light that's being given off, it's actually matter. A small amount of matter it's given off, and that matter gets highlighted as it leaves the sun, and it creates what we see as the corona. So these are the 6 layers. These are the 6 layers. 3 interior, 3 exterior layers. Okay. Is there any initial questions about the anatomy of our sun here? Let me know if you do. Okay, we're going to get into the interior of the sun. So let's start to do that. No. How about we clear out and stop and let's go. All right. Now we're going to start with the interior of our sun. Remember, these are details that I'm going to describe here that are basically true of all other types of stars, with minor differences that I'll highlight to you as we get to the end of the discussion here. But to understand what's going on inside of stars, there are 2 main ideas that you need to keep in mind. And these 2 ideas explain the vast majority of how stars work. Well, it's actually 3 ideas. Okay, it's 3. That's not 2, it's 3. Okay, idea number 1 is nuclear fusion. You got to understand that, and we'll talk about that. You got to understand how the structure of our sun looks. Well, how does it maintain its structure? And then the last thing is, how does energy flow in these areas? Those 3 things are basically all you need to know for how the interior of stars work in general. Let's start with the structure. Our sun and the vast majority of other stars are in what's called hydrostatic equilibrium. It's also referred to as gravitational equilibrium. And so what it says is simply this. At any given layer inside of our sun, there is a balance that is occurring. The balance exists between the weight of all the layers above that area of the sun and the gas pressure that pushes out to support the weight of that. Ultimately, the energy from this pressure comes from the fusion reactions and the energy and how it flows out to the surface. But this is the balance that objects have. This is very similar to how, pressure works in the ocean. As you get deeper and deeper down in water, the pressure increases because you have a balance of the weight of the water on top and the water pressure pushing back up. And that's the same thing is true of our sun. Okay. Now what this means is as you get deeper down near the core of our sun, there's going to be an immense amount of pressure, temperature, and density. These properties are required to be very high because there's an enormous amount of weight that pushes down on an area very close to the center of our sun. So the conditions require that all these properties, temperature and pressure, things like that, need to be higher. As you get closer to the surface, things relax because you don't have as much weight of material, and so you don't need to have your temperatures to be as high. You don't need your pressure and your density to be as high. But this balance that exists is how our star and most other stars are structured. They're structured like this. Another aspect that's important to understand what's going on inside of our sun is to understand how energy flows from the core out to the surface. It's this energy that powers the support of our sun and what ultimately makes the sun hot and shine and give us light. In physics, we are aware of three major ways that you can move energy. Okay, one is called conduction, which is energy transfer because things are in contact. So in the picture they show here, it's a weird drug reference, and I don't understand why they chose to put a spoon over a candle flame, because that's kind of like a trope in movies if somebody's gonna like do drugs or something. But anyway, it's also apparently how we teach physics. So, but if I were to for some reason put a spoon over a candle and I don't have any illicit materials in that spoon, then eventually as I hold it, it's gonna burn my hand. You know, a better analogy is when I cook and I just stupidly leave the ladle in the pan, and next thing I know, I go back to touch it and I burn myself. And part of me is mad that I burned myself. The other part of me is like, physics, that's cool. I burned my hand because of conduction. So anyway, that's a very important process on Earth. Things being in contact, you touch something that's hot, touch something that's cold. Just turns out for stars, it's not a very important energy transfer. It's slow, it's inefficient. The other two are much more adept at transferring energy. Another one of these is radiation. That just means movement of light. Walk outside and you feel the warm sun on your face. That's a radiation transfer. That was light that was emitted 8 minutes ago or so from the sun. Hit your face, warmed you up. That warmth came from the sun. Right? That's radiation transfer. And then there's convection, which is energy flow because material is able to freely move. A good example of this is when you put a pot of boiling water on the stove and you turn it up, you'll notice that the water, when it starts to boil, when it's a very vigorous boil, it looks like it's bubbling, right? And that's because the bottom layer of water that's in contact with the pan, that's the hottest, which causes the water to get a little less dense and it rises to the surface and it brings all that energy up with it. The cooler water eventually sinks down, gets heated up, and then it's just this like cyclic process. And that whole process of transferring energy because things are moving, that's convection. Okay? Heaters and air conditioners, that's convection. That's moving air to change the temperature of a room. That's totally convection. Okay. Convection radiation are very important. Energy transports inside the sun. This is why we have the names for these regions here. We have our core, and then right outside of that, where it's a little bit cooler, because the equilibrium dictates that, you still have a lot of pressure, a lot of density, and things aren't able to freely move. And so when photons are created in the core via fusion, there's only one way for them to get out. Okay, things can't move, matter can't move, so convection's out. And as I mentioned, conduction's not a very important process. It's incredibly slow. It's about radiation. So a photon is generated, and it has to travel through the radiative zone out to the convection zone. Once you get to the convection zone, conditions inside the sun have relaxed enough that that matter can move. In fact, we estimate that when a photon is generated inside of the sun because of fusion, it could take tens of thousands or even maybe 100,000 years to make its way out to the convection zone, because it's constantly going to experience, absorption, re-emission. Just it doesn't just travel in a straight line out. It constantly encounters other atoms, and it gets constantly absorbed and re-emitted, absorbed, re-emitted, absorbed, re-emitted. And so it makes this kind of drunken walk, which is actually a physics term. We say that when some things take a random walk, also called a Monte Carlo simulation. It's also referred to as a drunken walk simulation. So it's like this photon is just drunkenly trying to get its way out to the convection zone, and it could take an extremely long time. Like I said, it could be even hundreds of thousands of years. But once it finally does reach the convection zone, it warms up the gas that's there, like the bottom of the pan of water, and then that gas quickly rises to the surface. And that process takes a few hours, actually. So once you get to that convection zone, it's very easy to make your way out to the surface. So, the convection zone is just basically things are able to freely move. So you actually see a mix-in of gas. You see the warm gas rise up to the surface, stay up for a time, cool off, sink back down. I'll show you a video in a little bit of the surface of the sun, and it just looks like it's bubbling. I mean, the whole surface looks like it's a big pot of boiling water. Okay. So anyway, this structure that I'm showing you here, core, radiative zone, convection zone, that is the interior structure of our sun. It is the interior structure of the vast majority of other stars, with some exceptions, actually. Hold on here, sorry. Let me ask you a couple questions. You can either, speak up on your mic, or you can just type this in chat. But one thing we like to think about here is, what if we had a sun with a different mass? Because this is the structure for our sun. It's a one solar mass object. And what's important about being a solar mass is there's a certain amount of gravity, you can say, a certain amount of gravitational pressure that's generated that creates this structure. If we had a star with a smaller amount of mass and therefore not as much gravity, do any of you have an idea of how this picture might look different? At least in terms of like the size of the regions. Anybody have an idea? Do you have a guess? If I lower the mass of the sun, how does this picture change? Anybody? Shrink, Samuel. I like that. And you are right to some extent here. Now let's go back to this picture right here. Hydrostatic equilibrium. If I talk about a star with less mass, that means all these arrows that point down are now weaker. That means all the arrows that point up need to be equally weak. And that means you automatically relax the conditions inside of the star. It doesn't need to be as hot inside. It doesn't need to be as dense or have as much pressure. And so what that causes to happen is, yes, the entire structure, the whole star, is going to appear smaller because there's less mass, but the radiative zone is going to shrink in size, and the convection zone is going to increase in size. And that's all because the conditions are lessened. It's not as hot. This area right here, the boundary between the convection and the radiative zone, that happens at a particular temperature. But if that particular temperature now can exist closer in, that moves that boundary. The boundary moves. And so, for other stars, this is going to have some minor differences in appearance. Something special happens when you get down to 40% of the sun's mass. And we'll go into this more when we get into, the birth and death of stars. But when you get down that low, the conditions relax so much, actually, that the radiative zone shrinks and just poof disappears. And there is no radiative zone. It becomes purely core and then convection. So it loses a layer basically. And that's important because the way that our sun will die is dictated by this structure. And so these other stars that are small will die somewhat differently. They'll have a different fate. And again, we'll get into that when we talk about the death of stars. All right. Any questions about these ideas here? All right. So there's one more thing we got to talk about that helps you understand what's going on there. We're going to get to the core where nuclear fusion takes place. Okay. Nuclear fusion takes place. Now, the process of nuclear fusion that occurs in our sun is a very interesting interaction that takes place because it's one of the few places in the universe where all of the forces of nature that we are aware of have a role. In the list you see there are 4 fundamental forces of nature. We have identified that for the kind of conditions that humans live in, the universe demonstrates itself in these 4 ways. And the first 2 you are familiar with, gravity and electromagnetism. You know about these things. You experience them on a regular basis. Basically, gravity is very obvious. It's the force that keeps you on the earth. And everything else that you experience is ultimately electromagnetism. So when you sit in a seat and the seat supports you, electromagnetism. When you push on something, it's electromagnetism. When friction occurs, it's electromagnetism. Any kind of force is ultimately electromagnetism because it's an interaction between atoms. There are also 2 forces that you are not aware of because they only occur inside the nucleus of an atom and are responsible for the structure of atoms and the radioactive decay of atoms, and that's the strong and weak nuclear forces. These four forces are basically how the universe works. It's how the universe works. These 4 things dictate how particles interact with each other, which is really the basis of the entire universe. It's what is in the universe and what does it do. And these forces are what the things do. Okay. Now a question for you down here, just based on these descriptions. This is me asking you more of your opinion than you really to know this, because you won't. There's no way you can know this, but just your opinion here. What do you think is the strongest of these forces? And by the way, when I say that, I'm saying consider all things equal. What do you think is the strongest of these forces? What do you think? Put a letter in the chat if you could. All right. I see a bunch of A's. I love that you're saying A. And the reason why I love it is because you're wrong. And I like it when you're wrong sometimes. Not on tests, but when we talk, because that means you're about to learn something. Now, I know why you said A, right? Because you may have fallen down and hurt yourself, and you're like, damn it, gravity. Right? I mean, that's the one that feels the strongest. But it's deceiving. Gravity is not very strong. It only seems strong because the Earth has so much mass to it. Okay? Imagine this. Imagine I had these things here. My kids had these. These are some kind of like, when you play bingo, it's like how you blot. It's like these paint blotters. And, they both have mass. So, how could I somehow measure a gravitational force that happens there? Let me pin myself here. Like a look at my pretty face when I talk, I guess. All right, so these blotters here. Imagine These were magnets. Imagine these were pieces of iron that were magnetic. That would be an enormous interaction, right? Just think about big magnets. Now, with those magnets, how would you even measure a gravitational force? It's almost impossible. The gravitational force between these two objects is so small. I could calculate it, but I don't think I could measure it. I don't think it's measurable. It's out of the bounds of what we can detect, honestly. So the strongest of these forces is actually the strong nuclear force, and it's kind of the reason it has the name, strong nuclear force. The reason we know it's stronger is because, well, I just demonstrated that electromagnetism is actually a lot stronger than gravity, and gravity is deceptively strong because it is there's so much mass to produce a strong gravitational effect. Electromagnetism is definitely stronger than that. And then we know actually the strong nuclear force is even stronger than that because the strong nuclear force is basically what holds the structure of an atom together. Atoms, the nucleus of atoms have protons. They don't want to be around each other. They would fly apart if they could. And they don't, because there is a stronger force that glues the nucleus together. And that's how sometimes we refer to the strong nuclear force. It's almost like a glue that keeps the nucleus of atoms together. And that actually is the strongest force. The weak nuclear force is responsible for radioactive decay. That's basically when sometimes you can break that glue structure. And that happens by another force there. So anyway, my point in mentioning these is that all four of these play an important role when it comes to understanding fusion. So let's look at it. Okay, so I'm about to click forward here, and I don't want to scare you, but you might get scared. Oh, wrong slide. All right, gonna edit that out. Okay, that was the wrong slide. Next slide's scary, so go grab a helmet or something in preparation for the next slide. But the process of nuclear fusion is taking lighter elements, smashing them together so that they are bounded by the strong nuclear force and creates newer, heavier atoms. And that binding that takes place when you actually collide nuclei together and they sort of glue onto each other, that actually releases energy, releases a ton of energy. And that energy is what ultimately is generated by our sun. It powers our sun, it gives it its temperature and its light, and it's the energy production in really all stars. And the primary way that's done is by hydrogen converting to helium. So that's the first element on the periodic table being converted to the second element. That produces a ton of energy. Okay? That's what our sun does exclusively, almost exclusively. Like 99% of its interaction is that. Most stars, same deal, exclusively hydrogen and helium fusion. Some more massive stars could take heavier elements and fuse them into bigger things. And you can do that to an extent until you reach iron. Now, iron on the periodic table is like fourth level, fourth row. Atomic number, I believe, is 26. You can smash atoms together and make things up to iron, but iron becomes a sort of a limit. Iron has a very strong binding energy to it, and you really can't get energy out of that. You can't smash things together with it or break things apart to produce energy out of your interaction. Yeah, iron's 26. So it's considered to be in some ways the most stable atomic nucleus. It's really not possible to get energy out of it. By the way, all this stuff I'm talking about is distinctly different from fission. Fission is the opposite process by which you take heavier things and break them into pieces. And when breaking things into pieces, that can release energy as well. And that's called nuclear fission. Nuclear fission is not important in astronomy at all, pretty much. It doesn't power stars. It doesn't really power anything. It just exists, and it's mostly irrelevant. All right, here we go. Fusion. Now, I mentioned what our sun does. Our sun converts hydrogen to helium to produce energy. And that's hard to do. Hard to do. In fact, I will demonstrate to you. Ready? I'm going to try to do nuclear fusion right here. I'm going to attempt nuclear fusion for you. Now, if this works, the video might cut out. And you might see a flash of light even from your room. So apologies in advance. Ready? I'm going to do it. All right, I failed. Thank goodness. I tried, though. This is me trying. I tried. I tried to take the atoms in my hand and smash them together. That hurt a little bit. Smash them together to produce a nuclear fusion reaction, and it failed. And it's important to know why it failed. Okay, the reason why it failed is that the electromagnetic force prevented me from getting any closer. I can't get any closer than this. The electrons that make up the cells of my skin are pushing back. They're not allowing me to go any further here. And we call that the Coulomb barrier. That's the natural electromagnetic repulsion that exists between protons. In particular, this is electrons. Okay, me trying to do this is electrons saying, I don't think so. Coulomb barrier, go back. Now, inside of the sun, your atoms are really stripped away of their electrons. It's so hot, they don't really have their electrons anymore. It's just these free-floating protons. And when two protons try to get together, the electromagnetic force says, nope, slow down, fly apart. However, there is a certain temperature, there's a certain speed, I guess you could say, that you could shoot two protons at, that they may slow down, but they could actually hit. And if they hit, that's when the strong nuclear force takes over and binds them together and creates a new, at least isotope of hydrogen, at least in this case here. That's overcoming the Coulomb barrier. And that's what's needed for fusion. The reason why this didn't work is because basically the temperature of these atoms are not high enough to overcome the Coulomb barrier. It also means I'm weak. Because if I was strong enough, I could teach better. Or something. I don't know. Okay. So this process is what happens inside of our sun. Our sun, at the core, is hot enough and dense enough that when two protons try to collide, they do collide. And this process here is referred to as the proton-proton chain. If you look at the bottom here, this is the basic reaction. It's 4 protons are fused together to produce a helium atom, a bunch of energy, and these little things called neutrinos. I'll talk about those in a little bit. But that was what goes in, that's what comes out. And the only thing missing from that basic reaction is how you even get it to happen. You got to overcome the Coulomb barrier. You got to smash things so hard that they fuse. It's a 3-step process. Now, I'm not too interested in you knowing every little detail of the process. There's 2 things that you need to get out of this that you need to remember and you need to learn here. What goes in, what comes out, and what is required to make this happen. The details of the reaction I'm going to go through, but they're not the most important thing for you to know. Okay. It's a 3-step process. Each step of the process adds a piece to the nucleus. You got your 2 protons to start off with. Again, they overcome the Coulomb barrier, they smash together, they produce a neutrino, an anti-electron called a positron, that becomes energy almost immediately, and deuterium, which is an isotope of hydrogen. Once enough deuterium builds up, it collides with additional protons to create a gamma ray, and then they fuse to create actually a brand new element. And this is helium-3, 2 protons and a neutron. Now, it's not an incredibly stable atom, but it stays around long enough to combine with itself, with another one just like it, to produce, to basically spit out the protons that were introduced in step 2 and to fuse together to create a brand new stable helium-4 nucleus. So this process is what takes place inside of our sun. These protons are fused together in these 3 steps to make helium. Again, what ultimately comes out is a bunch of helium and a lot of energy. A lot of energy. Okay. Now, let's look at some numbers behind this stuff, actually. And, oops. What did I do here? Let's look at some numbers behind this energy. If you actually look at what goes into the reaction, the 4 protons, they have more mass than what comes out. The helium nucleus that comes out is different. 4 protons go in. What comes out are 2 protons and 2 neutrons, all stuck together. And the difference between the two is related to the energy that was released. We have to go back to Einstein's famous E equals mc squared equation. We look at the difference of the masses between what goes in and what comes out, and the difference is the amount of energy that was released. Well, it turns out that if you do the numbers here, and again, these are not details that I want you to be able to replicate. I just illustrate a point here. The mass difference between 4 protons and a helium nucleus is 0.048 times 10 to the minus 27 kilograms. It's a little less than 1% difference in mass. If you put that through E equals mc squared, you get what effectively is a trillionth or 4 trillionths, 4.3 trillionths of a joule. And, that's a very small amount of energy, but it is only one interaction. Now, this joule right here, this little tiny number that's in the trillionths, well, this reaction happens so frequently that what eventually comes out of the sun is this number down here, 4 times 10 to the 26 watts. That's joules per second. That's the luminosity of the sun. That's the brightness of the sun. That's how much energy the sun is releasing as a result of it being generated. The amount of energy that the sun releases is the same as the amount of energy it makes. It has to be. Where does the energy go, right? So how do you go from that one reaction to this 10 to the 26? The way you do that is you have to do this reaction here 10 to the 38 times per second. And when you do that, you convert 5 million tons of mass into energy. And the 5 million tons of mass and energy is the 4 times 10 to the 26. That's a big number. 10 to the 38. I have never figured out a way to properly express, at least concisely express how big that number is. It's an extraordinarily big number. It's absurd. In fact, if I was in your seat listening to me talk, my initial reaction would be like, that's BS. This is too big. I don't even know the name of that number. And I played a venture capitalist, but I don't remember the name of all the numbers. It's almost unbelievable. How do we know that's taking place? I mean, because in a way, you can argue, I just kind of backtracked, right? We measure the luminosity of the sun. Therefore, well, the reason we know is because of these neutrinos. With these neutrinos, there's two made every reaction. So there's 10 to the 38 reactions taking place. There's 10 to the 38 neutrinos coming out of the sun. Well, we figured out ways to measure that. And guess what we get? 10 to 38 neutrinos. So it's an extraordinary number. It's extraordinary reaction. It's mind-boggling how grand it all is. But our measurements verify this is exactly what takes place. We have the ability to measure neutrinos, and that's the number we get. So, all right. Any questions about this process? All right, so let's get a little bit into the exterior of the sun. Give me a second here. I'm gonna do one thing. Okay, great. All right, so exterior. This is stuff you can see. I can show you pictures of this stuff. Here's the first thing, photosphere. Now, you're going to start to see a lot more pictures in this class because we're starting to get into the topic of stars and galaxies, and so there's a lot more images from telescopes and satellites that you're going to be seeing. Obviously, you saw a ton of things in the solar system lecture, but now you're going to see a lot more. And you know a lot about how light works now, and so you can start asking yourself questions about what you see. Every time you see a photo, there are a couple questions you want to try to be able to answer or to at least inquire about to help you understand what you're looking at. First thing you want to figure out is, what's the wavelengths of light that I'm seeing here? Because, human vision is between 400, 700 nanometers, but we have telescopes and satellites and other things that can detect outside of that range. So sometimes when you see an image, it may represent a wavelength of light that you don't normally are able to see. Now, for this particular picture, this is what you would see. This is actually a visible wavelength picture. It's a broadband visual wavelength picture. It's just a telescope with a filter on it. It doesn't use anything special. You just look through the eyepiece and you would see this. It dims the level of light enough that you can see features. And in fact, this is an image that you would see if you look, with the telescope. You'd see this picture here. Now, the other question you want to be able to ask yourself is this: how is this light made? We're receiving the light, but it's important to understand how the light was generated. Now, this is photosphere, and so this is actually thermal radiation. This is the sun being hot and dense enough to produce radiation at all wavelengths. The thermal radiation we've talked about in this class. Right? So that's the source of the light. So thermal radiation, visible wavelengths of light, and that's our photosphere. And the photosphere for the most part looks very sort of bland and uniform, but you do have things that pop up like sunspots, and we'll talk about sunspots in a moment here. This is the chromosphere of the sun. This is the first atmospheric layer of the sun. It lies right above the photosphere. And as you can imagine, this is not easy to see, actually. The photosphere is incredibly bright, and it outshines the atmosphere. Now, this picture is an ultraviolet image. So you wouldn't see this with your eye, but it's an ultraviolet image, and it's actually a filter that's specially designed to capture a wavelength of light that is absorbed in the atmosphere and then later re-released. And so if you select a filter, and this filter, by the way, selects one of the wavelengths of hydrogen that is very commonly absorbed. If you focus on that particular wavelength of light, then the photosphere becomes dark because that light's not getting out. It's being absorbed by the atmosphere. And then when it's re-radiated, we see the structures of the atmosphere. So it's a very clever technique where you specifically choose something that is generated by the chromosphere. It's my dentist. What are they calling me for? Oh, I have an appointment coming up. I'll call them back. They're nice people, I guess. Although the music they play, sometimes I'm like, what are you doing? It's like, stop. I like the place they play. And then the hygienist hums along to the music. I'm like, when is this going to end? All right. Anyway, so this is our chromosphere. What you typically see in the chromosphere are the different layers of activity that occur in the sun. Anything that's happening on the photosphere has an automatic impact. It can be seen in the chromosphere. So we see a lot of the sun's activity, flares and prominences, things like that. That's all found here. Here's another view of the chromosphere. This is something you can see during a total eclipse, because the moon is actually doing the blocking of the photosphere. And so you're just seeing some chromosphere peek out around the edge of the moon. This is a visual wavelength image. This is done with a telescope and an appropriate blocking filter. But see the color there? That color is hydrogen gas. Those are those three wavelengths that we talked about repeatedly. Those are the three we can see. So that color is the color. It's very If you see that kind of color, that's pinkish, purplish color, hydrogen. Hydrogen. All right, this is the corona. The corona is an extended atmosphere of our sun. This is also an ultraviolet image, but it's actually close to being part of the X-ray part of the spectrum. And as you can see, a couple things in the corona, very dramatic solar flares, explosions, or really, really, prominent solar flares that are occurring. Can be seen in the corona. It extends out much farther. As sort of a normal process, though, the corona kind of looks like this. This is during a solar eclipse, and it's a picture with a time exposure of maybe, I don't know, 10, 15 seconds, and it highlights this solar wind. If you see this corona here, it kind of looks like troll hair. You know, the little troll dolls? Looks like the wispy hair. That wispiness, though, is caused by particles being ejected from the sun and then sunlight reflecting off of them. And that's why everything looks like it's kind of being, strewn away, basically. These little strands of gas flying away. And that kind of highlights how the particles are being blown away. Sometimes you refer to this as a solar wind. So those are the three exterior layers. Let's go to talk about a photosphere a bit more, though. Here's the photosphere. Like I said, it's pretty bland in appearance. Got some sunspots down on the left there. Looks like another little sunspot down on the right. You also notice that a lot of times with sunspots are bright spots, not just dark spots. When we say sunspots are not only dark things, but there can be brighter things too. There's some bright patches that are next to these. They usually go hand in hand. But let's just focus on the normal stuff. So if we zoom in a lot, let's zoom in a ton here. We zoom in a ton and we get this picture. Now, just to give you a sense of how we zoomed here, imagine I zoomed in 50 times. Then you get this picture. And this picture you can fit like 2 Earths in this image, I guess. Or so. About 2 Earths in this image here. Now, there's something really cool about this image. This picture was a snapshot that was taken. And if we took this picture again in a minute, it would look totally different. In fact, what's better is to show you a video of this. So let me actually bring up a video of this. Give me a second to do that. All right, so this is a time-lapse video, basically, of solar granulation, the process by which the sun is releasing energy. I believe this is 2 hours of time compressed in 30 seconds. So, am I screen sharing? I think I am. Okay. So let me run this. No. Don't screencast this. Jeez. So it's kind of hard to see here. It's slow, but you're seeing a lot of movement. Again, like I said, it's 2 hours of time or so, compressed into about 30 seconds. But what you're seeing this granulation process. The way you want to think about this is, I mentioned before, this is like the sun's boiling. So there's like water, gas, hot gas rising up to the surface, cooling off and sinking back down. All the areas that are sort of very bright, whitish in appearance are the hottest areas. They just recently rose up to the surface. Areas that are darker are areas that are sinking down and they've cooled off a bit. So that's the granulation process there. But this motion is the normal process of the sun. That's the normal process of the sun. We call this granulation. The little bubbles, little zones of hot gas rising up are called granules. We are seeing the convection of the sun take place here. We're seeing all that gas come up from underneath the photosphere to rise up here and to cool off. What typically happens is one of these bubbles will come up to the surface, hang out there for 10, 20 minutes or so, cool off, and then eventually be displaced by other hot gas coming up, and eventually will sink down where it gets reheated and it comes back up. A granule itself is very large. It could be hundreds of miles across. In fact, the average size of a granule is that's the size of Texas. It's actually a huge, huge bubble of gas. And this is normal. This is how our sun releases energy. Energy is generated from the core, eventually gets out to the convection zone, and this is what we see. We see the bubbling of the sun. But sometimes it doesn't always happen. Sunspots are areas where this convection process is disrupted. And this disruption doesn't allow the heat to flow here. It doesn't allow energy to move. Now, when you see sunspots, you typically see them as these dark patches on the sun. And that's deceptive because it's not to say that one, they're cool, or two, they don't even emit light. They definitely do. But in contrast to the surrounding area, which can be, I mean, the difference can be like a factor of 10 difference in brightness or more. The sunspots just end up looking faint in images because you can't collect enough light without oversaturating the rest of the image. So we're trying to highlight, like in the picture on the bottom left here, we're trying to highlight the granulation and then the disruption by the sunspot, but we can't take a picture long enough to actually really see all the sunspot. It's hot though. Lower 4,000s of Kelvin, which there are some stars that have that temperature, as for of its whole photosphere. So the question is, what's going on here? Why is it taking place? Granulation's not occurring here. Just to be clear about what's happening, let's go back to this picture right here. The normal process is a bubble rises to the surface, stays up for 15 minutes on average, cools off, is displaced, and comes back down where it gets reheated, and that cycle just happens forever. Sunspots are where a bubble rises up to the surface, and it stays, not for 15 minutes, but days, week, 2 weeks maybe. There's something that prevents the flow of the gas here. So we want to try to figure out what that is. One way to do that is to start looking at the atmosphere. Because the atmosphere, what happens there is a reflection of what's going on right underneath it. So we notice that when there's not a lot of sunspots on the sun, the chromosphere looks very calm and organized, clean, basically. These are X-ray images of the chromosphere of the sun. Now, in the late 90s, very, very late 90s is when sunspot activity started to increase in the sun. And this is a process that happens every like 11 years or so, where sunspots kind of come to a maximum and they reset and they kind of come back to a maximum. So during the late 90s is when the sunspot activity started to increase. And we start to see our chromosphere get more chaotic. It's blotchy. It's like there's like curves, like a twisting going on. And then the picture on the right here is chaos. There's a lot of sunspots were observed around this time, and we can see all of these what are called loop prominences. These are all pockets of gas that are coming up off the surface and arcing their way back down, and it's just traffic jam of gas here. So what's happening here? Well, there's a technique we can use, and we're not going to go into the details of this, but there's a technique you can use with spectra to measure magnetic fields. And what we find is that regions where there are sunspots are regions where there's a lot of the magnetic field. And that is actually ultimately what's happening here, is that there are regions in the sun with an enhanced magnetic field that becomes so strong it prevents the motion of the gas. Now, when you think of magnetic fields, you think of like, magnets. You stick them on your fridge or something like that. That's a type of magnetism called ferromagnetism, and it just exists between materials that are magnetic. But we're talking about electromagnetism here, and that is magnetism that occurs because of the motion of charged particles. And the sun, at times, can create a very complex motion to its particles, which can enhance the magnetic fields to a point that it actually starts to create problems. Starts to disrupt the normal flow of things. This picture here is an X-ray image of a sunspot region. The sunspot region is right in the bottom right here. And it looks dark because it's not producing a lot of light. What's happened is the magnetic field is not allowing gas to sink back down. Just stays there. A little delay in the camera here. It's kind of fun. Anyway, and that gas doesn't have a lot of places to go. And sometimes what happens is the magnetic fields can be so strong that it actually can rip the gas off the surface where it will collide down in another area. And that's a very common appearance in sunspot regions. We call these things loop prominences or just prominences. This is gas that's actually being taken off the surface and put back down because the magnetic field strength is so strong. All right, remember, hot gas is trying to come up, cools off, sinks back down, but sunspot prevents it. So what's happening underneath? There's gas trying to get up, and it's building pressure. It's just building pressure. It wants to get out, and it can't. And what's going to happen is one of two things are going to take place here. You have a fight now occurring. Magnetic field says, everybody relax, everybody just stay on the surface, let's just cool off, don't do anything. And the pressure underneath is trying to break through because the sun's trying to cool off. And eventually one of the things is going to win. Now, what can happen is gradually over time, this pressure can just slowly start to displace the material that's there, and then eventually the convection process will just turn back on. That's kind of a slow process, takes place over the course of many days. That can certainly happen. But sometimes it becomes more violent than that. And what can occur is the pressure will build and build and build, and then it comes out all at once in an explosion, which is what we call an eruptive prominence, which is also known as a solar flare. So sometimes a lot of energy and material can be ejected from the sun because of all the pressure. It's like a pimple it's like the sun's got these pimples, we call them sunspots, and then they pump, and then stuff comes out. And that's very much true. It's pressure that gets released, and sometimes that can become dramatic. And that's exactly what's happening here. Dramatic explosion of stuff. And what I'm going to do is I'm not going to attempt to show you any more videos because I don't want to anger my laptop any further. It kind of calls the shots in some ways here. But what I will do is I'll drop this link in the chat. This is just, the link's also in the syllabus, but I put a lot of videos that I show in class on my personal AVC page. And there are a couple, if you scroll down here, if you go to the chapter 1560, there's a couple really great videos that show eruptive prominences, really dramatic stuff. So I recommend checking those out. Again, I don't want to attempt to show you a video through a video again because, yeah, that happened. Now, the effects of this ultimately is you have these eruptive prominences. So that would mean a lot of energy comes out, a lot of light comes out, a lot of matter comes out. It's actually referred to as a coronal ejection. It stands for CME, is what's called a coronal mass ejection. That's when actually some pieces of the sun actually come off because the explosion was so dramatic. Well, this steady stream of particles that we get from the sun, now that comes from the corona. That's the normal solar wind. But during these flares, they become more enhanced, and they can actually cause a lot of issues with us on Earth here. For example, I mean, you guys, most of you are too young to remember that, and it really even depresses me even saying that, but I got my first cell phone like in 97 or 98, 98? No, there's no way. Yeah, really? All right, it was like late 90s. And back then, cell phones were garbage. And they were like these bricks. They were huge. And they were like this size. I'm not joking. They're huge. And what would happen is, like, a lot of times they would stop working because there wasn't a lot of satellites in space to do the cell phone communications, and solar flares would happen. It would knock them out. So it was not uncommon that I had this phone and it just wouldn't work for several hours. It's because there's some solar storm that occurred. So that can happen, and radiation like this is harmful for people in the space station and stuff like that. So they have to have they have to like reinforce the spacecraft and protect against these rays. But one of the cooler things that happens actually are the effects of the auroras. What happens is we have a magnetic field here on Earth because of the motion of the core of our Earth here. And these particles that come from the sun, they're charged particles, and so they interact with our magnetic field. And what they do is when they encounter our magnetic field, which, by the way, is the strongest near the poles, they get trapped in the magnetic field, and they do these little loops like this. They loop around like that, the little helical loops. And that looping that occurs causes a lot of collisions to take place with our air, which is mostly nitrogen with some oxygen in it. And those collisions excite those atoms, and they produce emission lines. And that's what you're seeing in this picture up here. These auroras are actually emission lines that come from gas in our atmosphere that's being collided with by particles from the sun that are trapped in our magnetic field. And that's a normal occurrence if you're close to the poles. If for some reason there's a solar storm that's stronger than normal, and usually, for as long as I've been alive at least, there's been about one of these a decade where the storms are so strong that the auroras can actually dip down to lower latitudes and you actually can see them in the AV. There was about once a decade, I remember. There's usually some big storm, and then you can look to the north and you can see them. So very neat effect. All right. So that's